So now you can see this figure. Here, two species A and B are being contained in a single chamber, but they are separated by a membrane. A membrane. Okay. So when this membrane is removed, this separation is removed, or the partition is removed, you can see that the species A is getting transported into the region or domain of B. Similarly, the species B is getting diffused into the domain of A. Okay, so this is a very good example of diffusion mass transfer. Here, this is taking place because of the concentration difference. Because of the concentration difference. Now, we will discuss very important law, that is Fick's law of diffusion. The Fick's law of diffusion that states that the molar flux, molar mass transfer, the molar flux, we call it the molar flux. Molar flux means number of molecules per unit area. So the molar flux of mass transfer, that will be equal to minus dAB into dCA by dx, where dAB is known as the diffusion coefficient, or diffusion coefficient of A with respect to B, and the dCA by dx means the concentration gradient of A along the direction of x, along the direction of x. Similarly, we can write JBX is equal to minus DAB into DCB by DX. That will be taking place in the opposite direction of A. So dCA by dx is known as the concentration gradient, and the dAB is known as the diffusion coefficient of A with respect to B. So the value of dAB will be depending upon the type of species A and B. And this equation is very much analogous to our heat transfer equation. You must be remembering the conduction equation, the heat flux. Heat flux is equal to minus K into dT by dx. It is very much analogous.